So, hello students, welcome to lecture number 2 of Advanced Semiconductor Devices KEC 056. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. Okay. So, in today's lecture, we are going to discuss an interesting topic related to energy bands and energy band diagram. So, let us start. So, when we discuss about or when we want to study the behavior of a subatomic particle like an electron inside a crystalline solid, we can't take help of classical mechanics or Newtonian mechanics to describe the behavior of electrons inside a crystalline material. Okay. Here we have to take help of quantum mechanics and we solve what is known as Schrodinger's wave equation, which is nothing but an energy conservation equation. So, that is solved for every electron and we find that every electron can be described by a potential function. Okay. Now, we have to go slightly back and you may have studied before in some of the previous courses that electrons have a dual personality. They can be considered as a particle, but they also behave like a wave at times. And when they behave like a wave, the so called matter waves given by de Broglie. So, these waves must have some wavelength, some frequency, some momentum and some energy. Okay. So, the aim of solving Schrodinger's equation for every electron is so that we can find out these kind of properties related to every electron. One important characteristic of any electron which is bound to an atom or bound within a finite space is that electron can take only discrete values of energy, that is energies are quantized. Okay. So, if you have a positive nucleus, the electrons can revolve around this positive nucleus in circular orbits and in each orbit the electron is considered to be stationary. By stationary we mean that it has constant energy in each orbit. Okay. And once an electron makes a transition from a lower level to a higher level, it requires energy, and if it falls from a higher level to a lower level, it releases energy. Another aspect is the Pauli's exclusion principle, which says that only one electron is allowed to occupy any given quantum state. What is meant by quantum state? You have 4 different quantum numbers n, l, m and p, your primary, azimuthal, spin and magnetic quantum numbers. The value of these quantum numbers for any electron is basically the signature of that electron. Okay. And Pauli's exclusion principle says that no 2 electrons should have exactly same values of these quantum numbers. So, taking into account these things as background, number 1, electrons are discrete particles, but they also behave as waves. Second, electrons are allowed to occupy only discrete levels of energy which are provided by Schrodinger's wave equation. When you solve Schrodinger's wave equation for every electron, the solution basically helps you to provide the level of energy which can be occupied by any electron. Thirdly, Pauli's exclusion principle, which says that no 2 electrons will have 4 sets of quantum numbers. Using all these 3 as basis, we can now proceed further to discuss about the energy band formation in a crystalline solid. Okay. The figure which is shown on your screen basically shows that for a single atom, you have an electron cloud occupying that nucleus, okay, and electrons are occupying discrete energy level. So, this x here, which you see this x here, this is the location of the nucleus, and going upwards on the potential scale or energy scale, electrons are located at some well specified discrete energy levels. Okay. So, we can't say that they can occupy any energy level, that is not possible. Okay. So, only these discrete energy levels are being occupied. The ones which are closest to the nucleus are the most tightly bound, and as we proceed upwards, this attraction, Coulombic attraction from the nucleus tends to reduce. If you solve Schrodinger's equation for an atom, the potential energy term takes into account all these electrostatic interactions, and the solution of this equation provides several quantum numbers. And after that solution, we can say that the potential profile of an individual atom looks something like this. Okay. So, this is how the potential profile of an individual atom, how does it looks like. Now, this is for an isolated atom, okay. And we know that any crystalline solid will have infinitely large number of atoms, okay. And when these atoms are brought together closer to each other, they start to feel the presence of each other. The potential profile of a single atom starts to interact with the potential profile of another atom, okay, and they start to interact and they start to overlap. In this case, the so called valence electrons, the electrons in the outermost shell, they are the ones which play a major role during interatomic interaction. Electrons are also known as fermions, and what are fermions? Basically all those subatomic particles which follow what is known as Fermi-Dirac statistics and obey Pauli's exclusion principle are known as fermions. Okay. Now, we know that discrete nature of energy occupancy can't be violated. Okay. So, even if all these atoms are very close to each other, their potential profiles are interacting with each other and they have to follow Pauli's exclusion principle. So, these things can't be disobeyed, okay. These constraints can't be violated. So, with all the valence electrons or with all the electrons of each atom, you cannot accommodate all of them at discrete energy levels, you would run out of levels of energies. Okay. So, for that we say that the energy levels start to split and you now have multiple discrete energy levels which are so close to each other that they now can be considered as an energy band. Like you have a range of frequencies known as frequency band, here we are discussing about discrete energy levels which are so closely spaced that they can be considered as an energy band. Okay. So, for an atom which contains electrons say up to the n equal to 3 energy level, okay, if these atoms are brought closer together, the outermost electrons in the n equal to 3 energy cell will begin to interact initially, so that this discrete energy level will split into a band of allowed energies. Okay. So, these allowed energies are still just solutions, quantum solutions of Schrodinger's wave equation, and they are so closely spaced that now we call them an energy band. For further reducing the interatomic spacing, we can say that the innermost electrons or the electrons of inner shell, they now start to interact and their discrete energy levels now start to split. And if the interatomic distance is sufficiently reduced that the interatomic interaction becomes very strong, so the innermost electrons are the last ones, but they can also split. Okay. So, to make sure that the discretized energy nature of electrons is satisfied, to make sure that Pauli's exclusion principle is not violated, we say that the discrete energy levels during interatomic interaction split and results in formation of energy bands. Okay. So, this is the basically the theory of how energy bands are formed. Let us try to identify or visualize this formation in terms of potential profile, so that we have a more mathematical solution. Okay. So, when an individual potential wells start to interact, the resultant potential of the crystalline solid looks something similar to this. Okay. So, this profile here which I am marking in red, this profile, this is for a single atom. Okay. This is how, when we go higher on the energy scale, this is how the potential energy varies. Okay. And this is for a solid which consists of large number of atoms. Okay. You see here inside each level the discretized nature is still maintained. Okay. But now you cannot say that an atom exists in isolation, it belongs to the material as a whole, right. And this is how the potential profile looks like. Now, I want to do a bit more of a mathematical analysis of this kind of a potential profile. For this, I use what is known as a chronic penny model. So, this potential profile on the left can be approximated by a well defined sharp boundaries like this, okay, where you can say that this is say region number 1, region number 2, which is again repeated, region number 1 is repeated, then region number 2 is repeated. Okay. So, alternatingly they are repeated. So, this arrangement can be approximated by a graph which is which has well defined sharp boundaries like this. Okay. So, electron can be confined within these wells, your so called potential wells, okay. And it becomes easier to mathematically analyze an electron inside a potential well. This approximation is known as 1D chronic penny model of the periodic potential function, and it is used to represent a 1D single crystal lattice. Okay. Here these numbers A and B, okay, this number which you say. So, let us see, we start from here, this is the origin, the distance of region 2, the length of region 2 is B and the length of region 1 is A. A plus B is nothing but the lattice constant of the material. Okay. What we need to do for mathematical analysis is we solve Schrodinger's wave equation in region 1 and region 2. Okay. Let us just see these symbols which are written here. H bar is reduced Planck's constant given by h over 2 pi. Psi or psi A or psi B is nothing but the wave function. M is the mass of the electron and E stands for energy. Okay. The wave function is basically which it is what it is, psi or wave function is what which you obtain by solving Schrodinger's wave equation. When you solve this equation for an individual electron, you get psi as a solution of this equation, and this psi can be applied to things like a momentum operator to estimate the momentum of an electron, to an energy operator to find how much energy is possessed by an electron. Psi square gives you the probability density function, which tells you how much is the probability of finding an electron in time and space. Okay. So, inside region 1 we say that there is no potential energy component, it is said to be confined in that region. So, the total energy E is only because of the kinetic energy. Okay. So, the term on the left here, this is known as kinetic energy and this is total energy. Schrodinger's wave equation is nothing but an energy conservation equation, which says that total energy is composed of kinetic as well as potential. Okay. Inside region number 1, from x equal to 0 till x equal to a, there is as such no potential energy possessed by the electron, it only has kinetic energy. Okay. The solution of this kind of a standard differential equation is given by this form. Okay. So, when you solve, you get a solution for psi wave function given by a, which is a constant, sin alpha x plus b another constant, cos alpha x, where alpha is equal to square root of 2 m e by h bar. Again, E is energy, m is mass of electron, h bar is reduced Planck's constant. Okay. Inside region number 2, from minus b to 0, we say that electron has both kinetic as well as potential energy, and this potential is given by potential value V naught. Okay. So, both kinetic plus potential, these two energies are equal to the total energy. The solution of this kind of a differential equation depends whether E is greater than V naught or E is less than V naught. If E is greater than V naught, this beta constant here can be written as square root of 2 m E minus V naught by h bar. Okay. If E is less than V naught, we get a complex solution. Okay. So, you use an I here. So, these two differential equations or the Schrodinger wave equation, when you solve them, you get the value of, okay, this there should be a b here. Okay. This is psi b, okay, wave function in region number 2. When you solve these equation, the certain solution which you obtain, okay, requires some boundary conditions. These boundary conditions also apply to wave function. Basically, wave function has to be continuous, the differential has to be continuous, and inside the infinite space psi square becomes equal to 1. These are some of the boundary conditions. In addition, to solve this chronic penny model for mathematical analysis of energy band diagram, we say that the wave function at x equal to 0 is equal to the wave function of another region, region number 2 at x equal to 0. If you see this potential profile, from this edge if you see, or this edge if you see, the potential at this point is same as potential at this point. Okay. So, this is a sharp boundary. Okay. So, at the edge of two regions the potential profile remains same. Okay. And if this is the same, we also say that the differential of wave function is also same. Third boundary condition is that in region number 1, if you are measuring wave function at say any value x equal to a, the wave function in region number b at x equal to minus b is related by an exponential term. This is known as Bloch's theorem and is useful for analyzing periodic patterns or periodic functions. Okay. And the fourth boundary condition is basically coming from the third condition only. We just simply see the differentials are also equal at x equal to a and x equal to minus b, and they are related by a exponential term. Okay. So, if you go back to the potential profile, you see that x equal to a is this point and x equal to minus b is this point. So, you see a periodic arrangement, and this is where the wave function and the differential are related by exponential term. Here k, which you see, is nothing but wave number given by 2 pi by lambda. Okay. And this is basically proportional to momentum. Okay. And we will see later on that your energy band diagram is nothing but a variation of energy of an electron with k, which is nothing but momentum. Okay. Once you solve these equations with the 4 boundary condition, this is the kind of solution which you get. Okay. We only need to analyze the solution and not focus upon the actual derivation of this solution. Okay. So, we just say that the right hand side of this solution is a cosine term and the left hand side is a large term which has sines and cosines. Okay. So, you can see that the cosine of any function is limited in value from plus minus 1, but the left hand side, this term here, can exceed values of 1 and minus 1. The left hand side can allow values below minus 1 and values higher than plus 1, whereas the right hand side is a cosine function, okay, where a plus b is your lattice constant, k is your wave number. Okay. This is limited between plus and minus 1. What does this means? This provides a very important conclusion that when you solve this mathematical model for energy of an electron, of different electrons for different potential profile of each atom inside a crystalline solid, we say that only certain values of energy are allowed and all those which are not allowed are considered to be forbidden. Okay. So, electron inside a crystalline solid can only take certain allowable energy values, okay, and any other value of energy which is not allowed is said to be forbidden. And if we plot this energy with respect to k, this is the kind of shape which we get. Okay. Since all energies are not allowed and certain energy levels are said to be forbidden, this gives rise to what is known as energy gap in crystalline solids. Okay. So, this is how this function f of e, which is equal to cosine of k a plus b, where a plus b is nothing but lattice constant, k is wave number 2 pi by lambda. Okay. So, these regions here, okay, so say these regions here, these are your allowed energy levels. Okay. These are your allowed energy levels, and anything beyond these are your forbidden energy levels. These are the ones which are not allowed. Okay. So, when you bring a lot of atoms together to form crystalline solid, the discretized nature is maintained, but those discrete energy levels are very close to each other and they form an energy band, plus not all energy levels can be occupied by electron even if they are located inside an energy band. Okay. So, there will always be some kind of a spacing between consecutive energy levels or energy bands, which gives rise to what is known as energy gap. Okay. And if we plot this function, okay, E versus k, now if we plot E versus k, okay, using the equation which we have obtained from chronic Penny model, you would see that the energy has some kind of a parabolic behavior. Okay. So, that function which we have just seen, this function here, okay, when you try to plot this energy f of e with respect to k, you get this so called E k diagram, okay, and it has a parabolic behavior, and at every integral multiple of pi by a, sorry, I should say a naught, okay, where a naught equal to a plus b is nothing but the lattice constant. Okay. You see that there is a sudden jump and you see another parabolic behavior, okay, at about say 2 pi by a naught, and same thing here, minus 2 pi by a naught. Okay. Why do we see a parabolic behavior? Is because if you see the energy which can be given by p square by 2 m, and we know that k is equal to 2 by lambda, and lambda is h over p, de Broglie's wavelength. Okay. So, this can be written as p by h bar. Okay. And if I replace p in the energy equation, I can get k square h bar square by 2 m. So, energy E is basically proportional to square of my wave number or k square, and because of this you see this parabolic behavior in the energy profile or your E k diagram. So, your energy band diagram, and if you now try to expand this this parabolic behavior in the entire reciprocal lattice, in the entire k space, you are going to see a lot of parabolas in all the 3 dimensions which have a sudden jump in energy, the so called forbidden energy gap, okay. And the energy is going to have a parabolic behavior with respect to k, which is a measure of momentum. So, every energy band diagram which we see is nothing but a graph, a sort of a graph between energy and k, or energy and momentum. Okay. So, inside these bands we can say that electrons are moving with a certain momentum. Okay. And if we see, if we on expanding, if you see that this is nothing but a closely spaced energy levels called a band, this is nothing but a closely spaced level of energy called a band. These are separated by a certain energy gap which is forbidden. Okay. So, this eventually translates to a scene where you have a large energy band, another energy band separated by a energy gap. Okay. Electrons with a tendency to occupy lower energy level tend to occupy all the lower energy states, and all the valence electrons, this is where all the valence electrons are present. So, this lower end of the band is sometimes referred to as valence band. The higher energy level bands, which are generally empty, is referred to as the conduction band, okay. And these are separated by an energy gap, those your so called forbidden energies or energy gap, okay. And this can be written as generally as E c, this as E v, right. So, this is how you can mathematically relate to the formation of energy bands in a crystalline solid. Now, this value of E g will help you to differentiate between different types of materials, and a value of E g equal to 0 signifies a metal, A very large value of Eg signifies an insulating behavior and an intermediate value of Eg specifies a semiconductor. And among semiconductors, if you see a range of Eg, you can differentiate between how much energy may be required for electrons to jump from valence to conduction band. Okay. So, this energy gap is nothing but those energy regions or bands which are forbidden, mathematically forbidden by chronic Penny model. Okay. There are regions or bands which are permitted to be occupied by electrons, but they are located above or below the energy gap. The upper bands are usually called conduction band and lower bands are referred to as valence bands. When we write EC in an energy band diagram, that signifies the start of conduction band, and wherever we specify EV, we are specifying that level where the valence band ends. Okay. And this helps this band edge helps us to basically tell you that if you have same momentum at EC and EV, you are referring to what is known as a direct semiconductor, your LEDs, so called LEDs. And if the value of momentum at EC and EV is not same, these are your so called indirect semiconductors like silicon and germanium. The separation between the lowest conduction band and the highest of valence band is the band gap or energy gap. Okay. And near the band edges, the EK relationship which we have just seen on the previous slide is given by E equal to P square by 2 m star, where P is the momentum, okay, of an electron and m star is what is known as the effective mass and given by h bar square divided by double derivative of energy with respect to k. Okay. And this double derivative also has a term and it is known as band curvature. Okay. So, this is how we see that solids are formed inside a or energy bands are formed inside a crystalline solid. So, with this we come to the end of today's lecture. I have introduced you to the concept of energy bands and energy gap, where we say that when lot of atoms come together to form a solid, their discrete energy levels split in space and form a band of closely spaced discretized energy levels. These are the formation of energy bands. Mathematically, we can say that not all energy levels are allowed, some energy levels are forbidden, and this gives rise to the energy gap. Okay. So, with this we end today's lecture. Thank you.